So now let's start with the second paper, Scaling Law for Neural Language Model. This paper was recommended by one of our attendee, Jacob, but he's not here today. So I'm trying to present the work for him. But in case you're interested, please join our Meetup group, which is Speech and Language Technology Meetup group. And this event is sponsored by OLEWave Inc. The Scaling Law for Neural Language Model by Jared Kaplan, Sam McCandish, and their colleagues. It's not a fairly freshly brewed paper, but I think this paper has a lot of good insights. I think it's worth for us to give it a reading. Well, first of all, they also mentioned that, neural language model is widely used. It's interesting for us to study aspects of the training, inference, computation budget of this neural language model. But I guess that today I don't have time to go into every details of it, but I will try to share with you the conclusion the author obtained, and I try to give my short understanding of their conclusions. Okay, first of all, I think this is the most important, very, very important, the first one. I think the second one is also very important. If you are saying that, I forgot what you're talking about, but if you're able to take home two messages, that's enough. The first message is that the NLM, neural language model performance, depends strongly on scale, weakly on model shape. What does that mean? So the scale, it means these three parameters. The first is the model parameters. So how big the model is. Okay. How many number of parameters are in it? N. Or the second factor of the scale is the size of the data set. Say, how many terabytes does your text database have? D. So the third one is the amount of computational resources or time you attribute or contribute to this task. Okay, easy to understand, okay? Well, which is not that important is the depth or the width of the model. So you say, I got a billion parameter model. Should I make it more deep or more wider? Squeeze it or stretch it. So the author said it doesn't matter much, as long as you have a big model. Interesting. Well, the second most important take-home message is that the smooth power loss. I think this may be more important than the first one because they're also trying to shed lights on the future directions of deep learning using lots of resources. So they're proposing something called law. Remember the Newton 3 laws of force, right? Inertia, acceleration, or I forgot the third one. They're trying to develop some laws that are being developed in the physics into the machine learning domain, which is very interesting. And they're saying this is a power law. Remember, this is a power law. Okay. Universality of overfitting, I think this is a common sense, which means that if you want to increase your model size, for 8 times, you may not want to increase your data size by 8 times. you should just increase it by 5 times. So which means, so given certain amount of data, you should always use a bigger model to prevent overfitting. The bigger model prevents overfitting. That's the take-home message. Okay.
But when they say bigger, I understand it's like N and D here, but there's a difference between depth and width. Do they provide a sense of?
Okay, based on my 1 hour reading of this work, depth and width are not addressed. So you have, when they talk about size, they're talking about parameters, n. So, of course, depth and width together, they determine the size of the n, right? Universality of training.
Can I ask a question about that? I mean, suppose I was doing image classification and I did a logistic regression, but essentially I just made every pixel a feature. If I didn't have that many images, it would seem that overfitting would be like exceptionally easy compared to a smaller model. So when they call this universality of overfitting, I mean, are there some caveats there? I mean, I understand maybe we have to dive into the paper a lot. Maybe it's like you go into the paper for like a day to really break that down. But I'm just curious if they gave any hints about that.
Well, I sorry, I didn't quite get your question, but I guess you're sort of confused by the terminology by the authors.
Well, I'm just saying that when we're looking at the number of parameters and the amount of data, I mean, I easily overfit data.
Yeah.
Right.
Yeah.
And so to call it universality of overfitting seems to me that there has to be some conditions on it, because like Newton's laws don't have conditions because they're fundamental, but clearly this is not fundamental, right? There are conditions under which it's true and false. So the question is, do they give some guide rails on when not to do this?
I have to say that I didn't see it, so I didn't see carefully all the details of the paper. I didn't see any exceptional cases to their universality stuff. And to be frankly speaking, okay, I doubt this, okay, because they only tested on certain data sets. They haven't tested it on different data sets. As many data sets that has enough amount of proof to show that their conclusion is accurate. But my thinking is that, okay, these authors, they're not saying that we're just defining everything for certain, but they're just saying, okay, we're thinking this, or my understanding is that according to our results, the data set we are using, we're developing these type of rules, laws, things like this. And especially you can see that is a ratio n to the 0.74 divided by d. I think it's fairly dependent on the data set, right? If you change your data set, that might be 0.73. Yeah.
Okay. All right. Thanks.
But I think this one is a common sense to me, or it. I mean, always you wanna see if we can use a bigger model. Universality of training. They're saying this interesting thing, but I think it's not that convincing to me. They're saying that training curves follow predictive power law, which means if you're doing the log scale, you can see the training curve goes in a linear line or in a line, right? Power law becomes a linear in the log domain, which means you can consistently lower your loss, but your loss will go to zero at a certain time point, right? But how does that convert to the log domain? That's strange to me. But I guess that they're saying that at the beginning of the part, or the beginning iterations or epochs of the training, they're not saying the final. Okay. And also remember, I think also I want to talk about the transformer or BERT language model, BERT MLM master language model technique. So when they when they add the mask into the training, you can see the training procedure would suffer from the mask input, and eventually the training would end up with a loss, which is very far from zero, very far compared to the input without masks. So I think that would contradict with their power law of in the universality of training findings. Transfer improves with the test performance. I think this is also common sense too. So what they meant is that suppose you train on Wikipedia, that you transfer to sports news, and then they're saying that this incurs a constant penalty. But they didn't define what the constant should be, right? It's interesting. They say this is a constant, and then they saying that, but this penalty can be improved roughly in line with performance on the training set, which means that suppose your training set is bigger and you get a bigger model, the model's generalizability got improved, so it may suffer less when you transfer to another domain. Common sense. Sample efficiency. I think this is also common sense to me, which means large models are more sample efficient than smaller models. What this means, given enough amount of data, given the same amount of data, using smaller model to train should always be worse than using a large model. That's what it meant. Convergence is inefficient, which means I think this is a common sense to me. Probably I read too many papers before reading this paper. They're saying this. So suppose you're training a very large model, so let me start from the beginning. Suppose we have a fixed computational budget, so you can only use 10 GPU cards for 10 days. Should you train a smaller model with 100 epochs, or train with a bigger model with just 5 or 6 epochs? The answer is the latter. So training a large model with a fixed budget is always better, although it is stopped or significantly short of convergence. This is common sense to me, or I experienced that before. Optimal batch size. I think this is interesting to me. I will go to the section 5.1 to explain the details of it, because this is new to me. So they're saying this, the ideal batch size for training this model is roughly a power of the loss only. So which means what? The batch size could be changed, because I work in the speech domain. I think our speech people seldomly change the batch size. But these guys, OpenAI guys, they change the batch size. Let's go to section 5.1. No, that doesn't work. So any questions so far? Okay, they're talking about figure 10. So the gradable batch size. So gradable batch size, I think they're creating this terminology again. I think it means the optimal batch size. Okay. versus performance. So you can see the good batch size goes up together with the train loss, right? And they're saying that the critical batch size approximately doubles for every 30% decrease in loss. So, correct me if I'm wrong. I think they're saying that when your training goes on, your loss goes down, and what you should do is that you should improve your batch size by increasing it. So the end to the training, the more you to the end of training, the bigger the batch size should be. But I didn't read the details of this paper, so I have to dig into it later on. But this is a very interesting conclusion to me. I guess I won't go into the different graphs and the math. It's for people who are really interested into that. But I will go to the discussions. The first implication, I think this is very important, because scaling with the NDC are power loss. Remember power loss, okay? Which means that suppose you are increasing the data size by 10 times, because this is a log, right? You're not gonna be receiving 10 times loss reduction, right? You're only gonna get about two times loss reduction. So, and the thing is to transcribe, but the labor that used in the transcription is a linear law, right? So today you hire 10 people to label 100 hours. You wanna label 1,000 hours, you have to hire 100 people. That's linear. So this poses a very, very important issue in the AI or deep learning, because you're using too many supervised training data. So when you want to get a better model, so say you want to increase the model performance by 2 times or reduce the loss by 2 times, then you probably have to collect 10 times the amount of data, which is too much effort. Okay, somebody put on chat. The second thing I think is interesting is that our scaling relation to go beyond mere observation to provide a predictive work. So what does that mean? So they're also trying to do some Newton from the gravity stuff, thereby looking at apples falls onto his head, okay, shoes falls onto the ground. So can these authors, they're saying that can we provide some predictive framework for other researchers, for the community? This is why they're saying this, okay, we're saying this, say, proposing this power law into the training to see whether that fits to other scenarios. Other scenarios includes, image, audio, and the video, because this also only did experiments on text, right? And then I think the other issue they proposed or they point out, which is known to the community by a long time, so whether the reduction in the loss would be able to translate into the improvement on the relevant tasks. For instance, even before deep learning, people know that to train the language model, they train the n-gram language model, they're using the PPL, the perplexity, which is which is a kind of, you can regard it as it's entropy based objective function, which is in the same family of entropy loss. So when you improve the PPL, the perplexity, that doesn't translate to the speech recognition accuracy. So sometimes you increase the PPL by this much, and the accuracy you got from the ASR is this much. Same thing here, I think. Deep model can be trained with pipeline. I think I read this work a long time ago. Yeah, that's the Google's Gpipe. For those of you who are interested, I'm gonna type the name here for you. It's called Gpipe. So Gpipe means you can train a very deep model, which is not be able to fit into the memory of your GPU card. Say your GPU card only has 16 gigabytes, and the model would take probably 48 gigabytes, okay? What do? So Gpipe allows you to split the parameter depth-wise. So say, this is conceptually speaking, okay? So split your model from the bottom, middle, and the top lay blocks into 3 16 gigabytes blocks and fit into 3 16 gigabytes GPU cards. And these GPU cards can talk together or work together to finish the backpropagation. So the model parameter get updated. This is Gpipe. And what is also doable is the model parallelization for the wide networks. I think this thing got proposed by or used by Professor Andrew Ng back in 2014 or 15 when he did the deep speech one. They're doing this model parallelization. So when the network is wide, so on each layer have many nodes, okay, I can use GPU card 1 to calculate the nodes on the left, also node on the right, and use the GPU card 2 to calculate the nodes on the left, okay. And then on the next layer, suppose those nodes are not that correlated. You can use this result for this one and this result for the next layer, this stuff. Sparsity, this is known for us. Sparsity dropout can enable faster training because backpropagate needs to compute less amount of arcs. I think I'm gonna be stopping here. Any questions? Okay, I'm gonna stop the recording now.